Hello, my name is Adriano Popo from the University of Western Australia. I'm going to present the work Interpretable Survival Models for Predictive Maintenance. This is a joint work with Paul Castle, Janet Hahn, and Melinda Hodquisk. Our context for this work is from the asset managers that are interested in predict the failure of one specific asset, conditioned to the history, conditioned to the data. We agree that Bayesian statistics support this need. However, it is not being widely used in asset management, due to complexity or to lack of software to develop and use Bayesian methods. Moreover, there are few applications of Bayesian analysis in service reliability, so we are here to provide a good example. Also, the ability to convey uncertainty to decision makers will be a key feature in practical development of predictive models. Our aim, then, is to demonstrate the use of Bayesian analysis on an exemplar in-service dataset. We would like to compare these models and these results to the frequentist approach, showing the ideas that what we can do with Bayesian analysis and what we can do with frequentist approach. Also exploring the interpretability of these two approaches. But it's important to state that we are not here to discuss if Bayesian or frequentist is better. We are not going under the discussions of Bayesian versus frequentist. We already have a lot of the discussions on the literature from statistical point of view, from theoretical point of view, and this is not our aim. Our aim is to provide a good example with service data showing how to use Bayesian analysis and what we can achieve under this approach, comparing to traditional approaches like frequentist analysis. Our data is wasted water blockage data, where we have 44,800 vitrified clay pipes. Both numerical data and categorical data work as our covariates, and this data is fully described in this reference here. A briefly overview of Cox proportional hazard model that we are going to use in our work is the traditional Cox model, where we have the proportional hazard function and one baseline hazard function. This baseline hazard function here, we are going to consider a Weibull hazard function. So the hazard ratio given two different values of covariates is just the proportional of the parameters beta related to the values of these covariates. Also, our likelihood can be written as a product of hazard ratio and reliability function, which is simply the density function of our model for the observed variables, and reliability function for censored variables. Here we are only considering right sensor data. So we have our likelihood. This is the traditional way to perform a Cox proportional hazard model with the underlying Weibull distribution. For the Bayesian approach, we have in our model 28 covariates. You can saw in the list at the beginning not exactly 28. Yes, three continuous variables and 8 categorical variables. However, these categorical variables has more than one class, more than one category. So to build the model, we needed to change this to dummy variables, and we add one variable for each category unless the reference category. So this is why we have 28 covariates. Another common problem in the Bayesian approach is how to define priors. In our case, our dataset has almost 45,000 samples. So the prior here is not our main concern. However, considering that we have 28 covariates, we were thinking of, okay, we may need a kind of variable selection, so we decided to use the lasso regression penalization method, which implies that the priors for our beta parameters are going to be a Laplace distribution. With this idea, we are given a concentrated mass around 0 for the betas, so if they are different from 0, it means that we have a significant value for this parameter. To compute the necessary values, we are going to use Markov chain Monte Carlo approach, which is standard in the area and now available in many different packages, and from the generation data, the generation samples from the posterior, we are going to use this to compute probabilities of interest to perform estimations. Falling to our results, what we have? The 3 continuous variables and the categorical variables. Here we are only showing 3 of the 8 covariates, and as you can see here that we were talking before, for example, for installed baked variable, what we have is 1, 2, 3, 4, 5, 6, 7, 8 different parameters. For the reference category, we don't consider one parameter, so we need 8 parameters just for one categorical variable. In this table, we have the estimated value, confidence interval, hypothesis test from frequentist analysis, also estimated value by posterior mean, credible interval, and one probability here. We are going to discuss this soon. But look, this is not the estimation of the parameter, but the estimation of the hazard ratio. Why? We can look here, and already from this table, we can start to understand, oh, higher is the length of the pipe, higher is the chance of failure. But let me call attention for these values here. Under the frequentist approach, what we have for years 20 and years 30 is a bigger than 1, saying that these 2 years has higher chance of failure than the reference category. But both confidence intervals contain the value of 1, and the p-values are values higher than the standard 5% significance level, or even higher than 10%. So we would say here that, oh, this is not a significant variable. However, when we look to the Bayesian ideas, we have the credible intervals are in some way quite similar and also containing 1. But under the Bayesian idea, we can compute probabilities in the parameter space, which means we can compute the probability of this value be bigger than 1. So this is what we did. And when we do that, see here, 92% chance of be bigger than 1, 97% chance of be bigger than 1, where under frequentist approach we are going to say not significant. Here we are not only saying that it's significant, but we are saying it's higher than 1, and then these 2 years has more chance of failure than the years on Techno 10. If we look at small values of this probability, what we are saying, a value close to 0, so probability of be bigger than 1 is close to 0, which means probability of be lower than 1 is close to 1. Just simple the counterpart of this probability. And then we can say that over the years and the newest pipe, or those that was installed more recently, the chance of failure is small unless these 2 years. But if you look at the point values of this, they are quite similar from frequentist and Bayesian approach. Also, if you look at the confidence intervals, let us look here the confidence intervals. what we have, most of them are quite similar. Bayesian approach in red and frequentist approach in green, blue. So when we look this, what's happening here? What do we have? We can easily say that both methods are similar. The results are quite the same. Well, we have a good sample. So yes, we should expect these results. So we are not losing to use the Bayesian approach because our data is really good. However, if we have a small data set, probably we could use the Bayesian approach and adding the expert opinion, the engineering opinion, and have better results than the frequentist. We could. I don't know. This is not our aim in this talk. But here, look, we don't have any argument to say, oh, the Bayesian approach is worse. But we have one more interesting thing. Under the Bayesian approach, we were able to evaluate for each pipe in the dataset the hazard ratio related to the baseline, which means higher value of this hazard rate, higher is the chance of the failure of the pipe. And here is the 10 biggest values in our data set. And when we go there and observe these pipes, we had that 7 of them had a blockage. So what we are saying here, if we look at the prediction, the mean time to failure of our prediction and the observed time to failure, our prediction would be considered bad. Yes, this is another point. We are not trying to predict the exact value, but what we are saying here is which pipes are those that has more chance of failure. So for the asset manager, when he needed to decide which pipe he's going to verify under this approach, based on the data, we could easily select the pipes with higher chance and go there and check. Probably these are the pipes which are needing maintenance. So we can also do predictive maintenance, just looking and getting better ideas of which one we should look first, the ones with higher chance of failure. So this can improve the decision makers. So our conclusion is that the Bayesian Weibull proportional hazard model provide asset-specific interpretable results for predictive maintenance for this pipe dataset. The approach also got the same variables from the frequentist approach where the p-values were lower than 5%. So the Bayesian approach selected the same variables and a few more. We don't want to remove variables on our data. Remember, the asset manager has all of that variables and all of them are important. And we are considering this, and the interpretation and Bayesian analysis is providing us this. Also, we were able to give measure of uncertainties that are much easier to interpret for the asset manager. Probabilities is much easier to understand than a p-value. So, thank you. If you have any questions, please write to me or to Melinda. We are both happy to answer your questions. Also, we would like to acknowledge our collaborators in these departments and the Center for Maintenance Data Science, and Melinda for her BHP Fellowship for Engineering for Remote Operations. More details about our method and the full table of estimations are available in our paper. Thank you.